Lecture 6.2, Calculating Microscopic Current. We've already have defined macroscopic current. And the way we did this here is that we had a wire and there's an area right here. So this is the cross-sectional part of the wire here. And so when I look at the rest of the wire, imagining that we have a copper wire, there's going to be a cross-sectional where the charge is going to go through right in here. So what we're looking at is we're trying to calculate microscopically the number of charges passing through this area right here. So macroscopically, we know this. So we then say that we have that the current, which is typically defined as I, is then equal to dq dt. And so what this is telling us here is that this is the net charge passing through in a time dt. And it's useful to define this as delta dq dt instead of the infinitesimal. So once again here, current then, the way we define it is written like this. And if I look at the units, I see that a unit of current is a unit of charge per unit of time, which is then a coulomb per second, which is the same as 1 amp, which we typically write as 1A. So, what do we mean when we say microscopic current? So we have to make some assumptions. One, we have to talk about the individual charges, the electrons, and we have to make one assumption about their drift speed, and then we have to define a new quantity called the concentration. So we need to do some background before we start. So the first thing here is that we assume all charges have the same drift speed. And remember, we defined the drift speed as Vd. Now, all of the charges having the same drift speed, of course, that's impossible. but we're going to assume that they have the same drift speed, which tells us that on average, the electrons come down the electrical incline at the same speed. But it's a distribution curve. And so when I'm really looking at this thing, you could imagine that we have an incline. And as I look at this incline, it's going to look something like this. And as I'm looking at this incline, we have multiple charges. We have a charge here, 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 and they are all moving roughly with the same drift velocity. So if we were to do this statistically, then we would have some type of standard deviation of the mean to tell us what's the average and what's the spread over. But we're not doing that. So again, this is just the high potential. This is the low. And when they come down, we say that the average speed is the drift speed. And we'll go with that. So then the second thing that we have to do is that we need to define a material dependent quantity. So a material dependent quantity is the concentration of charges in a unit volume. Again, that has to be on average. So if I'm looking at this, we could then say that now the concentration which we're going to define as little n, is then equal to the number of charges in this unit volume. That's how we talk about that. So if I was to draw a picture of the scenario, I imagine that we have a wire. And then we're looking at some volume. So in this case, we're looking at this particular volume. And we could see here is that in this volume right here, we have a number of charges. So this density of charges is the concentration. And so when I look at these units, the number of charges has no units. So this has inverse of 1 over volume, which is meters cubed. So now we're here where we need to be. We're now looking at the derivation of the microscopic current. So to derive this, current we use the current definition, where we then say that we're looking at the microscopic which is then going to equal to that amount of charge per that unit time. So we want to do this in steps. So the first step that we should start with is that we want to look at the volume spanned by moving charges in a time dt. And that's we're going to find out what that time is right there. So then the second thing here is that now we're going to need the total charge passing through a cross-sectional area in the wire. So once we have that, now we have everything together here. And so now we can calculate the microscopic current, and something new here, that's the current density. They really are one and the same. So let's look at these pieces here. So the first thing that we want to do is that we want to talk about the spanned volume by moving charges. As the charge moves through the wire, it's going to spend out of volume because the charges are not moving single file, they're spread out. So as charges move through a wire volume, it spans the volume where the cross-sectional area A and the horizontal motion of a charge. So when I'm looking at this, I imagine that we have this. We have No, I wonder if I can use this thing right here. Yeah, I think I'm gonna use this. So if I'm looking at this guy, I have this wire. And so I'm gonna make this a little bit bigger just so it could be easier to deal with. So in order to get a volume, we need the area here. And note that that's the area of this wire, or the cross-sectional area. Now, these drift charges are doing what? They each have a velocity that's equal to the drift velocity or the drift speed. So as this charges is moving per unit time, note that this guy right here is then going to be the horizontal distance that the charges move. So if I look at the volume spanned by moving charges, we could then say that this has to be the area times the displacement, but we know here is that this has to be the area times the drift velocity times the time. In other words, the span spaced by this charge is then going to be, you know what, I did not finish drawing this. It's going to be the area times the drift velocity times my time interval here, which I'm going to say is dt. So now we want to deal with the total charge. From the definition of the concentration, I'm then going to see that N is a constant because that's a material dependent thing. So if I want the number of charges in this concentration, I have to multiply it by the charge. So what this is saying right here is that this is the number of charges within some volume. So that has to then be how much charge is in the spanned volume divided by the volume spanned by charges. So if I manipulate this equation and solve for n, so solving for the total charge within the spanned is then, I'm just going to solve for dq here. Then I'm going to see here that I'm going to get dq, which is now the amount of charge in this spanned volume. And it should be Q times N. So when you're looking at this, note that this is the total concentration, right? This is per unit volume. However, that doesn't tell me about the number of charges. This should then be multiplied by the spanned volume by the charges. So if I'm looking at this thing, we really need to know what that spanned volume is, but we just calculated that. So now we get to the microscopic current. And so when I look at this microscopic current, I'm now really looking at this. I'm saying that the microscopic current is equal to dq dt. And that, and by the way, this is of the spanned volume. So then I start to then say, so what is dq? Well, that's going to be q times n times delta v of the spanned volume by moving charges. All divided by the time. So now I could just start putting this in. So what do I know? I know that then this guy has to be the charge E, the concentration is N, the volume has to be the area, and we calculated this quantity up here. We saw that the area is going to be the area times the drift velocity times the time, which then tells us that we write drift velocity times the time, but then we're dividing by that time. So right away, these guys cancel out, which then tells us that we have NE VDA. Let me be careful. Yeah, that's right. This is then going to equal to I microscopic current, which is of course also equal to dq dt. So before I leave here, there's another useful quantity. And this useful quantity is the current density, which is defined by the symbol J. And so when we look at this here, we then say that the current density which is J, is then going to be the current divided by the area, which then is NE VD. Now, as a side note, why would we even care about the current density? we are headed towards Ohm's law. Which has a microscopic and macroscopic form. So if I look at the microscopic, we then say that it's going to be E is equal to rho times J. If I look at the macroscopic, it turns out that it's the voltage is equal to the resistance times the current I. And this is what we call Ohm's law. So what we're going to find here is that in this form, this is why we want the current density. The current density is useful in this context.